Okay, so last week we calculated the volumes of solids when revolved about the x-axis and the y-axis. Let's introduce a second curve where if we did introduce a second curve that was being revolved about the x-axis or even the y-axis, it would create what's called a washer. And those familiar with what a washer looks like, it just has a hole in the middle. So this is what we're going to be working with. And if you can visualize this, all this means is that this region will have a hole in the middle. And that's what our cross-section will look like if we were to revolve about the y-axis. If we were to revolve this about the x-axis, it would simply look like this. So there's a single cross-section of a washer, and that's important to visualize here, because if you remember the formula that we're using is volume equals pi r squared h, the formula for the volume of a right cylinder. But because we're creating infinitely many cylinders, we're adding together infinitely many things, and therefore we have an integral from a to b. The elongated s represents a summation that we're adding together infinitely many things. That pi is a constant multiple. The radius with respect to x, that's if we're revolving about the x-axis using disks. And h is dx, the height of that cylinder, the width of each subinterval. So visualizing this will be important with our procedure on how to calculate the volume using washers. And this region that we're going to be working with, to begin, is the region bound by the graphs of y equals x and y equals x squared. And that's a pretty straightforward region, simply to help us with the procedure. So here's what our region looks like. Here's the graph of y equals x and y equals x squared. Let's first, before we do anything, revolve this about the x-axis. So we're going to sweep out the top function about the x-axis, creating a solid. And that will look something like that. Okay, so this now will have a cross-section that looks like this. Okay, so now there's a big solid being revolved. Our representative rectangle for that region looks something like this. Okay, let's fill that in with the color, tell the pop. Whatever color that is, green. So that representative rectangle, which is being swept out about the x-axis, is creating a solid with a single cross-section that has a width of delta x. That width of delta x tells us that we're using x limits of integration, and we're going to have an integrand with respect to x. Now, if we were simply to create the volume of this solid, well, that would be pretty straightforward. It would be y equals x squared. The one thing we haven't done yet is calculate the intersection points. The intersection point for these two graphs is x equals 0 and x equals 1. Now, I'm saying x because of the width of this subinterval. Let's sweep out our second region, which is y equals x squared. And that will look something like that. And we're going to have a similar cross-section here. We'll just pretend that this is all an intersection point down there. Excuse my artistic ability. Now, our representative rectangle for this region will look something like that. And we'll use a different color there. Let's use, I think that's red, whatever color that is. So there's our representative rectangle, which also has a width of delta x. And good thing, because we can't integrate with respect to x and then integrate with respect to y within the same interval. We would have to break that up and integrate separately. So now what's happening here is that the outermost region is being revolved, creating a solid. Then that second region is being revolved. And think about it as a knife going into the solid and cutting that region out, creating a hole for a single cross-section. A single cross-section here will look like this. Let's create a cross-section right there. So here's our outer radius, and our inner radius will look like this. So there's a single cross section, and I'll color that in so we can see it. Let's use that. And we're looking at that from the direction of the x-axis. So we're looking into this thing. And now there's a lot going on here, but all that happened is our outer radius was being revolved. That's this representative rectangle. Our inner radius was then being revolved. That's this representative rectangle. And that representative rectangle is that hole right here. So the formula for washers is outer radius minus inner radius. It's as simple as that. In order to create that hole, you're subtracting the volume that's being removed by that second curve. So in this case, what we have is pi times the integral from 0 to 1, because that's the intersection point, and we're using x limits of integration because of our delta x width of each subintegral. So pi times the radius with respect to x squared minus the radius with respect to x squared dx. Okay, our outer radius, and remember your radius always comes from your line of revolution. So which is the larger radius from your axis of revolution? In this case, it's the taller one, which represents y equals x. So we'll have pi times the integral from 0 to 1 of x squared minus the inner radius here is this function here. That function here is y equals x. And don't forget to square it. Okay, we'll just be setting up the integrals today. Although we will be responsible for calculating these integrals and evaluating these as a fundamental theorem in calculus. Let's say we want to revolve that about the y-axis. Well, let's first revolve our region. There's y equals x being revolved about the y-axis. And here's y equals x squared being revolved about the y-axis. Okay, so now our representative rectangles will look like this. And remember that your representative rectangles always come from your line of revolution. We're revolving about the y-axis, so begin drawing your radius from your line of revolution. So I'm going to keep going to my outermost function here. My outermost function here happens to be y equals x squared. However, that has a width of delta y. So if we have a width of delta y, that's telling us a lot. That's telling us that we want y limits of integration and we want a y integrand. Unfortunately, we have y equals x squared as our function. So we simply have to solve for y. Radical y equals x. And there's our integrands that we'll be squaring for the outer radius. This will be revolved about the y-axis. So our outer radius r of y, not r of x, equals radical y. Okay, let's create our second representative rectangle, which will look like this. And let's color that in. So there's our second representative rectangle, which again has a width of delta y. This is the function y equals x. So when we solve for x, we have x equals y. So our second radius, which is our smaller radius, equals y. So the region that we'll be revolving is this region here. Right there. And let's color that in a little bit. So there's the region that we're going to be taking to revolve about the y-axis. And again, treat this as two different equations, as two different questions here. Revolve the outer function, creating a somewhat of a bowl-looking thing, but a solid bowl with a solid top. And then you're carving out the inside until you get to the bottom. So what you're taking is the entire volume and subtracting that inner volume. So our integral will be as follows. We're going to have pi as a constant multiple, because remember, we're using the volume of a right cylinder, which is pi r squared h. The integral from 0 to 1. The limits of integration didn't change here. However, we are using y limits of integration. This ordered pair is 1, 1. Coincidentally, the x value equals the y value because we're working with the function y equals x. But be really careful with this limit of integration. It did change from an x value to a y value. This did change from an x value to a y value. Okay, so we're going to have our outer radius. Our outer radius is radical y, which is furthest from the axis. That's the curve and not the linear, and that's radical y. Don't forget the square. Minus the inner radius, which here is y. Don't forget to square dy. And that's how you use washers to find a volume of solid. And consider it as just an extension of what we already know. We're calculating two volumes, and we're subtracting the one that's being carved out from within it.